All right, we're going to get started. Welcome to the Mechanical System Design webinar. My name is Kent Esslinger.
And I'm Mike Mahoney.
And we are seniors on CUAUV, leading the mechanical team. We're both mechanical engineers graduating this year. So hopefully this time functions as a good way for us to sort of give an overview of what we do and what different options there are for overall mechanical system design. All right, we're going to take one quick break to make sure we're being heard. All right, sounds like we're good to go. So we'll be starting with our presentation.
Okay, so first of all, of course, this is supposed to be a time for you guys to ask us questions. So if you have any questions during the webinar, just send us an email at mrm257@cornell.edu, and we'll get back to you at the end of the webinar. But please ask us any questions that you have as we go along, because we really want you guys to get as much out of this as you can.
All right, so first, just looking at design cycle options. So we've noticed a few different ways of doing this, and our team has done complete designs in different ways. So the first is sort of a multi-year phasic redesign, and there's a good portion of teams at the RoboSub competition that tend to do this, and so it basically involves just adding new projects each year rather than doing a complete vehicle redesign. And so that is very useful because you can keep what worked, as well as being able to implement like new projects in a little less risky manner. If you redesign the whole vehicle each year, it's more risky. It's also easier on resources, shorter design cycle, because you don't have to worry about integrating every single vehicle component together.
Yeah, and then our team does an annual complete vehicle redesign. So that's a 12-month cycle. And it's good for training new members. We like to put all of our new members, our freshmen and sophomores, on completely mission-critical projects every year. And then by the time that they're done with their fourth year, they've done 4 different projects. And they've pretty much gotten a sample of everywhere on the vehicle. It keeps knowledge of each sub-team very current, as in basically we move people around. And as you go through, everyone sort of learns everything about every sub-team every year. And then, like I said, by the time your fourth year is over, you've got all that necessary knowledge to be a team leader. But of course, it does require a lot of resources in the sense that you have to make a whole new vehicle every single year. So we go through, and a lot of it is like time, man, resources, having to machine everything that we do and design everything again. And it is a little bit of a longer design cycle in the sense that every single year we have to go through a full 12 months in order to complete design and manufacturing of anything.
Cool. So these are some different design objectives that we focus on as a team, and it's also important to look at like the order of importance of these objectives, because sometimes we found that it's easy to get bogged down on things that might seem more interesting at the time, but in the end are not necessarily the most important objectives mechanically for the team. So we sort of laid out what we thought would be roughly the order of importance of what needs to be mastered in order to move on to like the next level of like focusing on different objectives. The first being sealing. So that's going to have its own webinar on November 15th, 11:15. So if you're interested in that, be sure to check that out. That's basically mechanically what we think is the most important thing, the bare minimum that has to be done mechanically is you have to be able to seal enclosures reliably and successfully. And so that's sort of the first main objective that needs to be focused on as a mechanical team. And that's what we, above all else, we make sure things can seal, and then we move down the list onto thruster layout and sensor layout, which are critical for being able to just simply like move in the water, and actually make it possible for your software team or whoever is doing that to create a controller that's even semi useful or good. You have to have a decent layout of thrusters and sensors to be able to do that. So then, next would be vehicle trim. So that's making sure that your vehicle can can hold its position in the water without being at a super funky angle. So being able to have your buoyancy at the amount that you want it to be at. We'll have a slide on that later. And then after that, moving on to more of the, I guess, like competition specific tasks with the manipulator and actuator layout. So after you have a vehicle that can actually move in the water with a decent thruster layout and all your enclosures are sealed, then you can focus on doing manipulation and actuator tasks. After that would be drag profile. So how, which affects how quickly you can move through the water in different directions. And then finally, weight savings and aesthetics. And we know that everyone, most teams would be able to identify these and focus on these. But we find it useful to just look at this list and sort of, check ourselves periodically throughout our design cycle to make sure that the amount of time we're allocating towards different tasks on the mechanical team actually reflect this, rather than thinking that we're doing it but not actually implementing it on the throughout our designs and throughout our design cycle as well.
So a little background about what we do on the team. Again, so there are 3 groups that we have on the mechanical team: structures, actuators, enclosure, and main hull. And like I said, we have a 12-month design cycle. So that goes everywhere from concept and brainstorming in August, where we actually go over virtual discussions and weekly video chats for brainstorming, design, modeling, and simulation in September and October. So basically when we get back to school, we'll start looking at designs and going through all of our design reviews with one another. And we have that on a 3 design review schedule. So we do preliminary design review and then a mid-level design review where we go over some of the things that have changed since PDR, MDR, and FDR we call them. And then by the time FDR comes around, final design review, we should be about basically done, and then we lock the designs and we start to move them into manufacturing, which is our November to February. And with that, when we do that is we have a machine shop here, and we'll go up to the machine shop and we all manufacture our stuff ourselves. And then starting March to May, we put the whole vehicle together, put it in the water, and then do testing and implementation with the software team and the electrical team and make sure everything's working right. And then, of course, there's summer testing, which is everything before the actual competition. And that's pretty critical because we get about 8 or 9 hours a day of testing in that. Of course, key objectives: keeping electronics dry. That's the sealing part. That's priority number 1. Optimizing ability to control the vehicle. That's thruster layout, sensor layout. Creating reliable task manipulators, again, the manipulation actuator, and learning and improving manufacturing techniques. And that kind of goes in with every year having to redesign and then go and manufacture everything yourself. We get a lot of experience in trying to figure out the best manufacturing techniques available to us.
All right. So looking at the systems on the vehicle. First is, so we split our mechanical team up. We have about anywhere between 10 and 15 members of the mechanical team each year, and we split ourselves up into 3 different sub-teams working on these 3 different subsystems. So the first would be structures. So that's, and below are just the simple requirements or objectives for each sub-team. So structures builds anything that enables us to mount all the different components onto the vehicle to provide rigidity and protection for key parts such as our Doppler velocity log, and responsible for trim and optimal controls layout. So basically the structures team is responsible for building the frame and any external enclosures for holding different vehicle components, allowing for accessible mounting, optimizing the layout, the overall drag profile of the vehicle. So it's mostly frame and enclosures that are involved on that subsystem. Actuators, so that's what it sounds like. So we have a mix of electrical and pneumatic actuators depending on the task. The sub-team is responsible for creating either the claws or wheel turn or whatever it may be for completing the competition manipulation tasks. And so traditionally we've done a valve enclosure and a sort of some sort of grabber, multiple grabbers, and then some sort of servo motor manipulator as well. And the thrusters are also part of the actuators team. Finally, the enclosures, or the main hull, or what we call the racks and caps team, is the third sub-team. So they are responsible for building our main hull, which holds all enclosures, or all boards inside of the enclosure, computers, cameras, all that sort of stuff in our main hull. We implement a design where we had the Doppler velocity log also inside this hull last year, which was pretty cool. So optimizing wire routing, connections, all that sort of deal, making sure everything's as accessible as possible for testing and visible, so that our electrical team is able to debug and access all their boards the best they can. And also how we seal this is quite important as well, and so they do a lot with that. All right, so we're going to be going through each of these three sort of subsystems and outlining some different ideas for how they can be done, different ways that our team has done them. We've seen other teams do them, just to sort of throw ideas out there. If you're looking for different ideas, and we'll give sort of our opinions on them. Of course, this is just what we've noticed. You know, of course, more research is always better in investigating these different designs. So we're going to start with the structures group. You can see on this slide, there's a number of different designs. So the most basic being on the bottom right-hand corner is a simple PVC sort of frame or structure. And of course, advantages of that is it's super lightweight, very customizable, very cheap. However, it can deform and be weak in some senses, not always the most reliable. Next would be something like 80-20, which is also pretty customizable. You can add brackets where you please. You know, if you haven't worked with 80-20, it's pretty easy stuff to customize to fit all of your different needs for mounting. However, it can be expensive, also pretty heavy, but overall it's a lot more rigid and of course structurally sound than PVC would be. Our team about 4 years ago used like a box tube sort of frame, and so that is very structurally sound. We used to say it could survive the down the stairs test, which means it was strong enough to you know, be thrown down the stairs and still survive. So it's much more strong. However, last time when we did that, the frame weighed about 18 pounds, and then when we moved to a design that was CNC'd, an aluminum frame, as you can see in the upper right-hand corner, we were able to cut the frame weight down to about 2 pounds. So obviously it's a lot heavier. It's also a bit more time intensive in terms of manufacturing. The box tube style is, but depending on what manufacturing techniques you have available, that might be a really good option. And then finally, what I just mentioned is like a CNC sort of design, or you don't even need a CNC for this necessarily, but any 2D profile can be water jet cut out of aluminum. So if you if you have somewhere where you can get that done, it's not always super cheap, but it's also not that expensive either compared to other design styles, or for instance, purchasing a CNC, of course, is ridiculously expensive. So doing something like you see in the upper right, we found to be very useful because you can optimize mounting locations. You can keep it extremely lightweight, and it's still very strong. We've never had any, like last year, for instance, we didn't have any issues with the frame breaking or cracking or deforming too much. So it's overall a pretty sound design. So these are just a couple of other things that we do on the structures team. So we have battery pods, which you can see in the upper left. And the reason we make these into separate enclosures is so that they can be hot swappable. So we generally have built 3 sets of 2 packs each, so that you can always have one plugged into the vehicle when you're replacing out packs. Then you just replace one at a time. So basically the vehicle doesn't ever have to turn off, and you can move on quickly with testing. So we'll generally have 3 of these packs so that we can always keep packs charging, and the vehicle can basically constantly run with 3 packs. It takes slightly longer to charge one setup than it's fast. It's slower charging one set than it is using a set on the vehicle. So that's why we have 3 sets. The bottom is a hydrophones enclosure, and that includes all of the electronics boards for our hydrophone system, as well as the elements, which are the three cylinders poking out on the side there, as you can see. We've put this away from the main hull of the vehicle, mainly because of noise reasons and with the actual boards for the hydrophones tasks. And then we want the elements to also be placed in an optimal location for the least amount of interference. So that's why we've created a separate enclosure for that, as well as the kill switch is obviously separate from all the electronics are separate from the main hull, so we can have it be accessible as possible. And next. So we talked about vehicle layout a little bit earlier. So we thought we'd do like a case study sort of explaining how we did things on Gemini, which is our vehicle for last year. So you can see on this slide that there's a side and a top view. And so I'm just going to kind of talk through the different, like the mindsets, I guess, and ideas we had for why we laid the vehicle out in the way that we did. So first, talking about thrusters, we've used a different number of thrusters throughout the years. And, you know, in competition, if you walk around, you can see many different thruster layouts, and actual numbers of thrusters on the vehicles vary a lot as well. So as we were thinking through this, we kind of went through like what we, I guess, would see as ideal or recommended for a different number of thrusters that you have available to you, because we know these can be expensive and, you know, like resource-wise, you know, and also like electronics-wise and battery-wise, there's a lot of different constraints that control how many thrusters you're actually able to put on your vehicle. So, for instance, if you had 2 thrusters, the best option would be just to have surge, obviously, so you can see on the top view are surge thrusters on the side that would allow you to move forward and backward, and have some option for movement in the yaw. However, not having depth control is very difficult. So, you know, 2 thrusters would be very difficult. So 3 to 4 thrusters is sort of what we see as like the minimum required for basic controls. So you can keep those 2 surge thrusters, one on each side or one on the top and the bottom, however you want to do that, as well as having 1 to 2 depth thrusters. So this offers obviously movement in the vertical direction, as well as giving you pitch control. So we try to, so this year we had 4 vertical thrusters, as you can see in the top view. In past years, we've just had 2. So when you have 2 vertical thrusters, we found that it's most ideal to put them as far apart from each other as possible on the fore and aft of the vehicle, so that you have optimal pitch control as well. And the other option would be to put them on the port and starboard sides of the vehicle, giving yourself roll control. But pitch is more important, especially for like camera viewing, and if you have torpedoes mounted somewhere on your vehicle, you want to keep your vehicle best position for that. So next, if you have 5 to 6 thrusters, that adds strafing capability. So you can see on the side view, we have a thruster on the fore and aft, allowing us to strafe, which is very useful for maneuverability. And then this year we actually had 8 thrusters on the vehicle, which was useful for having active roll control. So we basically had thrusters in all 4 corners, which allowed us to have very good pitch control as well as roll control, and move very quickly in the vertical direction, as well as maintain our two surge thrusters. So some recommendations for just looking at placement of that is be careful in your statics sort of calculations and diagrams and determining moment arms. So we spend a bit of time in doing that as we're laying out the vehicle. For instance, the height of the vertical thrusters or the pitch controlling thrusters doesn't matter if you think about the moment arm and statics. However, the height of the surge thrusters is important, so that your vehicle isn't pitching big time every time you move forward. Another thing to keep in mind is as we're designing the vehicle in the fall, we always have a buoyancy spreadsheet to try and keep track of roughly how buoyant our vehicle is going to be So we look at, so in SolidWorks, whatever CAD program you're using, it's very easy to see center of mass. However, what's actually important is center of buoyancy. Unfortunately, that's extremely difficult to find without a lot of work going through each of your parts, finding the full volume, the center of that, and then compiling that for the entire vehicle. So we sort of just go with the center of mass, and then also it's very intuitive, sort of balancing out the vehicle. But we take input from the whole team on that, and we know in the end that foam will have to be added, or weights if that happens to be your situation. Also, for us, we lost a vehicle about 10 years ago in the bottom of a river, so we always create our vehicle to be slightly buoyant, slightly positive. Yeah, so you can see on this design, as far as overall layout goes, the batteries were in the front because we were thinking they would be heavier. So like the valve enclosure was in the back, which was heavier. We thought that the rear, the aft hull would be slightly heavier as well. It turned out that we were a little bit off this year and had to add a lot of foam to the front because of the batteries being so heavy for the vehicle. So yeah, so we'll move on, I guess.
Yeah, so I'll talk about actuators briefly. Actuators is kind of a fun topic because for me, I was on it in my freshman and sophomore year, so it's definitely something that's close to my heart. But it's also the kind of thing where finally your vehicle gets to sort of show off what it can do in the water and doing different manipulation tasks and stuff. So just looking at a couple different typical actuator systems. Normally forward torpedo task, you'll see a forward torpedo. So you'll see torpedoes of different sizes and shapes, and they're normally just shot through different tubes. And one of the things that you'd like to do is to make sure that your torpedoes are near cameras, because the camera is going to be, what sees the actual object, and the closer the torpedo is to the camera, the better off, or the more likely that your torpedo will actually fire into the spot that you want it to. You can also look at the downward grabber, the recovery task, and there's a couple different options there also. We've seen in the past with Tortuga, University of Maryland, they've done sort of a passive grabber where they can actually go down and run into it. And we've done a passive grabber in the past too, where we just run down with little spikes and hope that our spikes will grab onto the thing that we're trying to run into, and then we can go maneuver over to the we're dropping off and then just wiggle the sub and let it fall off too. We also saw with University of Florida Subjugator, they had a actual deployment boom where the grabber was deployed further away from the vehicle, way down below it. That's also a useful task for if you're trying to get the grabber into the view of the camera that you're using, and then you can actually manipulate that grabber to be directly over whatever obstacle you're trying to pick up. And then we see right in the bottom right corner, a typical grabber that we've been using, just a piston that actuates with just certain geometries so that the actual little pincer will close. Additionally, in the past few years, the competition's been adding an element of forward manipulation, and we think that that's a pretty fun task because you get drive over to the middle of the pool in the middle of nowhere and then try to manipulate some cool stuff over there. So if you look at just typical things that we've been doing have been just motor enclosures, so servo enclosures that will rotate different obstacles around. So like 2 years ago, we saw a wheel and we had our servo enclosure just rotate a little pin there that will then rotate the wheel around. And then last year we had the servo enclosure that sucked in the reroute to power task. And then you also have droppers, which we've seen a lot of magnetic droppers that are held in magnetically. Our dropper, we just had in our actuator system a pneumatic system that will actually shoot a puff of air that will disengage the magnetic strip on the actual actuator tube. And then you also see in Sonia's AUV that they just have solenoids that will remove the magnet part away from their ball, and it'll just drop into space. The other really cool subsystem is Enclosures or the main hull. So the main hull pretty much does a lot for the vehicle. It's our main electronics enclosure. that goes on in part with sealing. You don't want that to flood. But there's a couple different options that you can look into for your main hole. So what you can do is you can basically figure out the different number of holes that you want to do, and also how many sensors you want to combine into your main hole. So you see sort of a one-hole design like University of Florida's, where they put most of their custom electronics inside there. Or actually, I guess it's a two-hole when you look at the DVL sensor. But they put all their custom electronics inside the first main hole, and then they have a DVL separately from that in their other hole. So you can see in front of their main hole right there, that's where they put the DVL. You can also put everything into one hole, like we and also Sonia do, where you would have both your racks. So you have different off-the-shelf components and also custom electronics, both in the same hole design. And then you can also have your DVL in the same hole. Something that does for us is we can actually reduce the number of external enclosures on the vehicle by having the DVL just inside the main hole. And then that also allows us to be able to put the DVL and everything closer to the ground. And what that'll do is that'll give us a little more active roll control versus passive roll control. And then you also saw Maladalin University. They have a really cool two-hole design where they put, separate all their whole component or electronics components into two different holes, and then they interface the two together. So just looking at our hole design again, so what we do is we put all of our custom electronics in one side of the rack or one side of the hole, and that's a hinging rack so that we can have the electronic engineers go through and actually mess with that stuff as they need to. And then we put the more off-the-shelf components that we don't think that we're going to need to touch very often in the other side, so at the fore rack. And what that does is it does allow us to be able to get into the certain parts that we need to and only unseal parts that we need to when we need to. So, for instance, the forward rack shouldn't have to be adjusted very often. So all we have to do is unseal the rear hole, and then we can get into the custom electronics. That just allows fewer points of failure for later on when we're looking at sealing as the main priority. One cool thing that we also do is a vacuum assisted hole. So what we do is we actually usually have a little 1/4 inch MPT in the back where we just have a little valve, and we'll pull a vacuum inside the hole, and we have a pressure sensor inside the hole. That way we make sure that at any time, if the pressure ever starts increasing after we pull a vacuum, then we know that we might be losing our integrity of sealing. And if the pressure starts increasing, then that's a sign that we're probably taking on water. So we would want to take the vehicle out as soon as possible. Also, one thing to think about is stereo vision versus not stereo vision. So in this case, we have two cameras, and that's for stereo vision. But if you don't have the capability of stereo vision and your software team, then you only do one camera. But it's just something that we've been looking into in the past. Another thing when looking at the main hole, you want to have, because of your hot components or your computer and a couple different components on different boards, you want to make sure that those are being circulated by fans somewhere in the middle of the hole that will get the hot air circulating to the aluminum parts, because those are better conductors than, say, our polycarbonate holes. So just make sure, some people might have just an aluminum hole all around, in which case you don't have to worry too much about fan movement or air circulation. But where the majority of your hole is acrylic, like ours, just plastic, you would want to move that hot air to the end caps. So we just use acrylic because we like to be able to actually look into we have a lot of display LEDs, so it'll tell us different statuses on different boards, and also we like to have LED strips going across the aft rack. And what that does is it tells us, while we're actually in mission, what's going on with the vehicle. So because we can't actually, during the final runs, figure out what's going on with the vehicle, any time that we might lose due to the vehicle doing something that we don't want it to is time lost from the final competition run. So what we'll do is we'll have LED strips that will flash in different colors, and actually sometimes a Morse code to tell us if there's actually something going wrong and if we have to pull it back or not. Just one other thing that we want to mention too is CCON. So the main hole is pretty much the receptor for all of the CCON and all your sensors going into the the from the outside of the hull into the main hull. So one thing I was saying was trying to get all your sensors into the main hull does allow you to reduce the number of outside connectors that you need to have. And that's just a cool thing to think about. If you can get like your cameras inside the main hull, like we have it, then you don't have to route CCON from the separate camera enclosures to your mid cap or your main hull. But it is just a thing to think about is your connector layout and stuff.
All right, so finally we have a just like overview of some different manufacturing techniques that we've used over the years and that we've seen. So starting off, so our team does most of our manufacturing in-house, and we've had a bit of success with that. We also, fail numerous times building each enclosure, which helps us to become, I guess, better machinists. We know that not, all schools have, mill lathe CNC use in-house or training available. So, somewhat different options that we found too are water jetting and laser cutting. So those are options where you're able to have 2D profiles. Actually, this year with our frame, we're going to be moving to water jet instead of CNC just to decrease the manufacturing time on it. And we're not actually seeing like significant enough weight savings using the CNC for it to be necessarily worth it in that regard. So 3D printing is another aspect that we've seen to be pretty useful for creating non-structural parts. Also, it's been great for us in the aspect of parts that definitely have maybe more complex designs that we don't want to just create out of like aluminum right away. We'd rather 3D print one and then test it, print another one, test it again, print another one. 3D printing can be great for that because it's generally pretty fast, depending on where you're getting it done, and not too expensive. So you can get a pretty fast turnaround time rather than going and, getting a really expensive, some sort of metal part made instead. So we found that to be pretty useful for non-structural parts. Carbon fiber is another avenue that we've been looking into. We created a shroud last year on the team. One of the seniors did, and he had a pretty big learning curve in terms of the amount of time and skill required with carbon fiber is we found to be very high, and it can be expensive as well. But it might be that is like the most optimal structural way to create strong structural members that are lightweight as well. And we're looking into that for frame design in the future, actually. But most of what we do is done on the mill and lathe, and we try and keep most of our parts aluminum if we can, so they can, for weight reasons, and also so that they can be anodized and protected from corrosion. Steel parts will only be used for extremely structural parts such as shafts, things that we can't have any deformation in. Any parts available or exposed to the water, though, are either anodized or there's some sort of there's a stainless steel or plastic. Due to the corrosion that we've seen in our pool and at Transdeck and wherever we're bringing our vehicle into lakes around here as well. So I believe that is it. If there are any questions, again, feel free to email. It doesn't have to be, if you're watching this video later down the road after it's been recorded, feel free to also shoot us an email. We'll get back to you as soon as we can.
We do have a few questions already. So one from Moon-Young Lee. You have recommended a minimal of 4 thrusters on AUVs. How do you go about determining the best configuration, position, or orientation of these thrusters to best ensure stable vehicle movement with minimal software support?
Yeah, so I guess looking at the options for 3 to 4 thrusters, we'll go back to that slide. Yeah, so obviously, so the 2 key things with that option is looking at having control, being able to surge with your vehicle, which is having, so the 2 different options for that, I guess, we'll run through is either having the thrusters on the top of the vehicle, top and bottom of the vehicle, or the port and starboard. And so that will allow you to have, we I guess have seen more value in having it on port and starboard, so then you can have a if you don't have any strafing capabilities, you're able to turn the vehicle by, of course, going like reverse with the port and forward with the starboard thruster, which is a good option for being able to turn the vehicle. If you have thrusters on the top and bottom, you'll have increased pitch, but that's not as valuable when you have two actual thrusters on the fore and aft of the vehicle for controlling your pitch and depth anyway. So as far as making it best for your software team to optimize their controls, it's really important to make sure that the thrusters are actually equidistant from the center, sort of the center line of the vehicle. As you can see in the top view, if you drew a line down the middle of the vehicle, having thrusters that are off a bit does not optimize the use of your thrusters at all. So keeping them equidistant, as well as keeping the pitch thrusters as far away from the center of the vehicle as possible, we found to be the most useful. So yeah, then the other part was what force calculations must be done, any software to help in this process. So looking at that, like I said, it is difficult to do effectively find like the center of buoyancy of your vehicle. We have started using a spreadsheet that basically we have every single person on the team fill out the volume and mass of their enclosure so that we can calculate buoyant force, and then from there we can sort of find the moment that's inducing on the vehicle by measuring moment arms in the overall CAD model to the center of the vehicle. So that is an option that we have started to do. It's very, very tedious to do that with every single vehicle component. But ideally, if that could happen, you would know exactly how much foam you would have to add on the vehicle, or maybe added volume to enclosures to make it so that when you put the vehicle in the water for the first time, you have it perfect. But in the end, adding foam is very easy, and it's a very convenient option for making sure your vehicle is trimmed properly to allow the software team to have their best bet at implementing proper vehicle and optimal vehicle control. Also, in the past, one thing that we've done is characterize all of our thrusters. So we'll take all the thrusters off of the vehicle, and we have a system basically with a long arm that the thruster attaches to, and then we have on the opposite end of the so we have like a fulcrum in the middle, and then the opposite end we have like a fish scale. Basically, it just measures how much thrust we're getting from each of these thrusters, because we found that some of our thrusters are not necessarily, so we use video array and Cbotics thrusters, and not all thrusters are created equal. So we found that it's important to to some extent characterize, are the thrusters actually giving us the same pounds of thrust given a set voltage and current input into the we might have the same current and voltage input into two different thrusters, but they're giving us different thrusts, which is also important for the software team to know as far as designing a controller for that.
Yep. Okay. So another question: what kind of airflow calculation does CUAUV do for the main hull to ensure operating temperature inside the hull is appropriate? So one thing we do have is a temperature sensor on our computer. That's pretty much the most important component that we want to keep cool during operation, because if the computer overheats, then that kind of fries everything up. We don't really do an actual airflow calculation. That would involve either ANSYS Fluent or different hand calculations that we don't quite have the capability to do, or either want to do, really, considering all the other stuff that we have to do for the vehicle. Pretty much what we've done in the past is put a lot of fans near those hot components, just making sure that the airflow looks like it's going to be, and again, it's a very intuitive process, just making sure that the airflow is going to get past the computer, the hot parts, and get that hot air to the different end caps. Another question is, how do you determine how effective the current cooling system is? Have you tried other cooling systems before? What was worse, better about it? Again, most of the time we just use the fans. We use different strength string fans around the different parts of the hull to make sure, again, that we're getting hot air to the aluminum parts of the enclosure. One thing we did try in the past, or at least thought about trying, was a water cooling system where we were actually going to route brass tubing, copper tubing through the inside of the main hull and actually route that to the hot components on the different parts of the vehicle, the electronics. But again, when we're considering sealing to be #1 priority, having a bunch of water running freely inside of the main hull doesn't exactly sound like a safe bet. So we decided to just stick with the fans because that's been working for us in the past.
Overall, we've had like very few issues with overheating components inside the hull. So if something's working good like that, then we're not going to go to great lengths to try and improve it.
All right, so it looks like that's all the questions we've gotten so far. Again, if you guys have any questions after watching this later on, just make sure to send us an email at any time. We'll definitely get back to you guys about that. I hope that this was useful for you guys. Ken and I genuinely love to tell everyone about our vehicle and help out when we can. So good luck out there, guys.
All right, over and out.